Hi, everyone. Welcome to today's Colchin seminar. It's my great pleasure to introduce Ivan Tomasic and his talk about Galois theory of differential schemes.
Thank you very much. Thank you very much to the organizers for inviting me to speak, and also to everyone who's joining the seminar. So I would like to tell you about the Galois theory of differential schemes that I worked on with my colleague Behrang from Queen Mary as well. Before we start, I'd like to give you an idea of the extent of generalization that we managed to achieve. So the classical Picavecchio theory is pretty much about the extensions of differential fields, where the base field K is extended by a fundamental system of solutions to some linear differential equation, and then you form this Picavecchio extension, and then inside there you have the distinguished Picavecchio ring. And so in our generalization, we replace the fields, which here I've drawn as points with a kind of vector. Fields with a derivation geometrically look like a point with a vector. We replace fields with differential schemes, which here I'm representing as manifolds endowed with vector fields. And so the Picavecchio ring extension is, in our generality, replaced by what we call a Picavecchio morphism of differential schemes. And you see, in the classical theory, the constant field is replaced by something we call pi zero of x, the categorical scheme of leaves. And the classical fact that the Picavecchio ring is a simple differential ring is replaced in our theory by the notion of the top scheme being categorically simple. And the key innovations which allow us to achieve this generalization is to consider differential schemes. I'll explain what they are in a minute, but to consider them on one hand as pre-category actions. So to each differential scheme, you can assign a kind of pre-category element inside ordinary schemes, which allows us to tap into and develop the theory of descent in differential algebraic geometry, to speak about this categorical simplicity, and to use categorical Galois theory in this context. On the other hand, it is also very useful to consider differential schemes as actions of the formal additive group GA hat. And you see here we had the notion of this pi zero, of this categorical quotient, but in practice it is very difficult to verify that something is a categorical quotient. So we developed the theory of geometric quotients, where your essentially idea is that you're thinking of the quotient of x by its formal group action, and a geometric quotient is going to imply categorical quotient. So in this way, we obtain effective criteria for checking that something is a categorical quotient, and for this categorical simplicity, which gives us the opening into many, many applications. So out of these applications, I will try to explain how to, first of all, clarify the classical Picavecchio correspondence in terms of quasi-projective quotients of this affine scheme, the spectrum of a Picavecchio ring, which many of you know as a torsor for the PV Galois group. but we cannot somehow remain in the category of affine schemes and just work with rings and fields. We really need to extend the PV correspondence to quasi-projective quotients. Then, because we're able to work over a scheme, over a constant scheme, we can think of this scheme as the scheme of parameters, and we can treat parametric systems of differential equations. And a very beautiful concrete application of this was kind of clarified to me by Sonia Rueda, that basically we now would like to apply our machinery to spectral problems of commuting differential operators, where you know that a key object that appears is this so-called spectral curve. And in our context, this can be the categorical space of leaves of some universal solution scheme. So, and then for the final application, I would like to explain how to consider the canonical Picavesiot-Galois groupoid of a linear ordinary differential equations. Many of you will know that when you're constructing a Picavesiot extension, there's a non-canonical choice to be made. Now, all the resulting Galois groups are going to be isomorphic, of course, but you might be kind of unhappy for having to make the non-canonical choice. So in our context, we can consider a groupoid where the objects are these choices, different choices of Picavesiot extensions, and the object of morphisms encodes the isomorphisms between the different Picavesiot extensions. So I hope to come back to this at the end of the lecture. And I'll start with the very quick overview of the classical Picavesiot theory. So as I already mentioned, we start with a differential base field, K. Then we take a system of linear differential equations, adjoin a fundamental system of solutions to obtain this Picavesiot extension, but we have to do it in such a way that the constant field is not enlarged. And in there somehow lives the Picavesiot ring, which is an integral domain, and its fraction field is L. The Japanese school of Hopf algebraic approach to Picavesiot theory tells us that we can consider the tensor product of A with itself, A tensor A over K. We take the constants of that. We obtain thus a Hopf algebra over the constant field, and then taking the spectrum gives us the linear algebraic group, which we dub the Picavesiot group. So the classical Picavesiot correspondence tells us that there is a one-to-one correspondence between intermediate differential field extensions here and closed subgroups of Zariski closed subgroups of the Galois group G. Genelidze created this very general categorical Galois theory where pretty much you can start with just an arbitrary adjunction and define elements of Galois theory. And he noticed that his very general template can be applied to PV theory if you take the following adjunction. So we have the category of differential rings, op, and category of rings, op, so opposite categories. And then the left adjoint is taking the constants of a differential ring, thus obtaining just a ring, and then the right adjoint takes a ring and assigns the zero derivation on it. So when you do this, the categorical Galois groupoid, which is obtained from the general template, agrees with the previously obtained PV group. And however, there is a little twist. Generalizze really emphasizes that it is the Picabessio ring that is a key object and not the Picabessio field extension. So when you try to answer a question of Akira Masuoka, does the categorical theory recover the classical PV correspondence, you realize that the answer is no, because you cannot somehow only consider affine quotients of this A. You have to start considering quasi-projective quotients, and therefore you want to generalize this adjunction. So when we talk about differential schemes, what do we mean? Of course, we can work over an arbitrary base scheme S, and then an S differential scheme is simply a scheme over S with a given S derivation on its structure sheaf. And in algebraic geometry, it is well understood that a derivation of the structure sheaf gives rise to a vector field on the scheme. So we can kind of imagine differential schemes as manifolds endowed with vector fields. This gives us the category of S differential schemes. And of course, we have this functor, which takes an ordinary scheme and makes it into a trivial or constant differential scheme by giving it the zero vector field. And that is somehow the right adjoint that you'd like to have. But the problem that you soon encounter is that this functor does not admit a left adjoint. So in order to solve the problem of the non-existing left adjoint in general, we consider the notion of the categorical scheme of leaves. So you want this categorical scheme of leaves to be the somehow universal morphism into a constant scheme. So if you have a morphism into a constant scheme, which is universal from X to C, meaning that for any other morphism into constant scheme factors through Q in a unique way, then we proclaim that Q is the categorical scheme of leaves or the categorical quotient of X. The trouble is that this rarely exists, so it doesn't exist as a scheme for completely arbitrary X, and therefore only provides a partial left adjoint to C. This is how you can sort of imagine this categorical scheme of leaves. X, with this derivation, has, of course, a vector field on it, and such a vector field will induce a foliation, and you're asking that the space of leaves has a structure of a scheme. So clearly, this is a very big ask. It's kind of not so easily satisfied. So that kind of gives you an idea why these things rarely exist. Now, what we'd like to do is develop as one of the major components of our work a theory of descent in differential algebraic geometry. In order to do this, I need to explain internal pre-categories and their actions. So given a base category A, which for us is later going to be the category of schemes, a pre-category, an internal pre-category in A is a diagram consisting of the following objects and morphisms, where you're thinking of C0 as object of objects, C1 object of morphisms, and here you have the source and the target maps. So to each morphism, you can assign its domain and you can assign its codomain. And then this is the identity section, which to an object returns the identity arrow on it. And then this C2 can be thought of as the object of composable pairs. Now, such a diagram will be an internal category if this C2 actually is the object of all compatible pairs. So basically, here we have the source and here we have the target map. So you're talking about all pairs FG such that the source of one is the target of the other, so they can be composed. So if every compatible pair can be composed, then you have a category. A pre-category is something more general. So we allow an arbitrary object here and a bunch of morphisms where this one should be thought of as the composition morphism. And they satisfy the expected relations. There's another way of thinking about pre-categories. If you like simplicial objects, then you can think of this as a truncated simplicial object, where here you would have more maps and more degeneracies, but at the top level, we did not include the degeneracies here. So a typical example, which appears quite a lot in our work, but also in the theory of descent, if you have a morphism in the base category, you can create the kernel pair groupoid in the following way. So the object of objects is X, the object of morphisms is X cross X over Y, and this is a triple fiber product. Now, of course, you can think of this as X cross X over Y, cross X, X cross X over Y. So this is really a category. It's even better than just a pre-category. So what we'll do later is we're going to apply some kind of a functor to this diagram, and then it's not necessarily going to remain a category. And that's what happens. So if you're familiar with the theory of descent in classical algebraic geometry, you will know that you can only speak of descent of very specific data. And not usually, it's not the whole category of schemes and arbitrary morphisms of schemes that you can hope to have a theory of descent for. So we have to handle this in a suitable way. So we need this ability to speak about indexed data. And we choose to do this by, in the language of indexed categories. And so we give ourselves a pseudo-functor on the base category, which simply means that for every object of the base category, P of X is a category. For a morphism in the base category, you obtain the pullback morphism between P of Y and P of X. So this is a functor. Plus, you have to give certain coherence relations, which will deal with the pullbacks of the composite versus the composite of the pullbacks, and so on. Now, typical examples, which are very significant from classical theory of descent, even from as early as SGA1, the classical flat descent of modules would basically have as a base category the category of rings, and then P of a ring would be the category of all R modules. Second, which is somehow immediately derived from this theory of descent of rings and modules into schemes, is that you take your base category to be schemes, and for a scheme X, P of X is the category of quasi-coherent sheaves on X. And finally, one of the examples that we will consider later on, if you take a scheme X, then for P of X, you take the category of all quasi-projective morphisms with target X. For all of these examples, classically, we know the theory of descent for through Grothendieck. Okay, so for a given precategory in A and a given pseudo-functor in A, we can define the category of C actions in P in the following way. So the objects consist of a pair P0 phi, where P0 is an object in P of C0. Then phi is a gluing morphism living over C1 between the pullbacks of P0 to over C1 via target and source maps. Plus, when you now pull this into over C2 in 3 different ways, you have to make sure that this is all compatible given by a certain co-cycle condition over C2. So this is just a very general abstract descent data. Concrete descent data is a very similar definition, but only applied to these kernel pair. So for the case where C is a kernel pair category associated to a morphism. Okay, as I already mentioned, our first key observation is that differential schemes can be seen as actions of a particular precategory. So let's define this precategory in schemes over S with object of objects S, object of morphism S with when we adjoin an infinitesimal, so we want epsilon squared to be 0, and then the object of kind of composable pairs, the second level, is obtained by adjoining 2 infinitesimals such that also their product is 0. So this really is a precategory and not a category, because the category would not have this mixed term. So a key observation is that differential schemes are precisely the actions of this ds on schemes. And this gives us a beautiful translation mechanism. From a differential scheme, we can write it as a precategory itself, so it will have these components x0, x1, and x2. Using this translation mechanism, there's a beautiful description of the categorical scheme of leaves, and it simply becomes the scheme of connected components of the associated precategory. You see, so pi 0 of x delta is the connected components of pi 0 of the associated precategory, which is usually defined as the co-equalizer of the source and target maps. Co-equalizers famously don't exist in general in the category of schemes. So this is yet another indicator that you can't expect to have these categorical schemes of leaves in full generality. Okay, now this is the theory of differential descent that we are able to establish using the translation mechanism into pre-categories. So how do we do it? We start with some index data on ordinary schemes. Examples we've already seen. For those, we know classical descent theory. But what we do now is we extend this index data to a differential index data in a natural way. So for a differential scheme, we return as delta p of that the precategory of x actions in P. So this usually gives you some very natural class of objects. So for example, if for P you had these quasi-projective morphisms, then for delta P, you're going to get morphisms of the form Q delta to X delta, such that the underlying morphism of schemes is quasi-projective. So this is a very natural way to lift ordinary index data to differential index data. Now, of course, if this is a little bit more intricate, then this delta P might be something you wouldn't guess at the first attempt. So, but this is a safe way. I mean, in category theory terms, this is some kind of a Kahn extension, and it's the most natural way of doing this. So, when we start with the morphism of differential schemes, along which we want to study descent of certain data, it will, of course, translate into a morphism of associated precategories, and it will naturally break up into three components, F0, F1, F2. And our theorem is that the differential morphism F is effective descent for the differential data if F0 is effective descent for classical data, F1 descent for classical data, and F2 pre-descent for classical data. So we're able to use classical descent over schemes to study differential descent for differential schemes. Okay, we mentioned in the very beginning that we need to define categorical simplicity, which will kind of correspond to classical simplicity of the Picabessio ring. And actually, it's not so easy to do that. So this was kind of not a straightforward generalization that you might guess. So we say that a differential scheme is categorically simple with respect to some indexed data if it admits pi 0, it admits the categorical scheme of leaves, and not only that, it is universal with respect to this indexed family. So I don't want to bore you with categorical notion, what it means to be universal for some P, but you should think of a very familiar property that appears in PV theory. So basically, you want pi0 to be preserved by arbitrary base changes. And so you want to think of this condition saying that pi0 of x base changed to some q over its pi0, it's again q. So the conditions of this form are usually all over the classical literature. So basically, you will have something like constants of the PV ring, and then base changed over the constants to some other field. And they will say that this is now F. Okay, so this is a very familiar condition. All right, so as we already said, we have the categorical definition of pi0, but in practice, because it's only defined through the universal categorical property, in practice, it is very difficult to check that when you're given some example, that a certain scheme is the categorical scheme of leaves. So that's why we develop the theory of geometric quotients, and we consider differential schemes as formal group actions in the following way. So we say, okay, differential schemes in characteristic 0 are simply actions of the formal additive group on schemes. And I'll give these the easier direction. So when you take a differential scheme, how do you get the action of the formal additive group? Well, on the space of X, on the underlying topological space, it does nothing. But on the structure sheaf, it is a Taylor expansion. So basically, on the structure sheaf, you take your F, some kind of section of your structure sheaf, some function on X, and you assign to it a formal power series, which is its Taylor expansion. So a very beautiful formula. And now we want to somehow try to think of the quotient X by this action of this formal additive group. However, if you know about quotients in algebraic geometry, you'll know that this is almost impossible to define directly because, well, you have a formal group and it's very badly behaved. So we kind of model our notion of geometric quotient on Mumford's geometric invariant theory, but the conditions have to be appropriately modified in view of the fact that we're dealing with a formal group and not some kind of reductive or algebraic group. So, okay, we say that a morphism from a differential scheme X to a constant scheme is a geometric quotient if we have a topological condition. So the underlying morphism is submersive. In other words, the topology on Q is quotient topology of X. We have the orbit condition, the kind of fibers of eta roughly correspond to some kind of closures of orbits of J hat. So these are kind of scheme theoretic orbit, and this is where we needed to deviate from the original definition. And we have a sheaf condition saying that the sheaf of the structure sheaf of Q is essentially the sheaf of constants on the push forward of the structure sheaf on X. So basically, you're sort of thinking that Q is somehow constants of A pretty much, but you have to express it in algebraic geometry terms. And there's a theorem saying that if you have a geometric quotient, it is also categorical. So that gives you now an effective criterion for verifying that something is a categorical quotient, because you only need to check the properties of the morphism itself. You don't need to check some very general universal property ranging over all differential schemes. So this is a lot more effective. And we developed a very useful criterion for checking it. And not only that, we have the following really useful theorem for checking that something is a universal geometric quotient, which will then give you the effective criteria for this categorical simplicity. So how does it go? Suppose you have a geometric quotient such that for every geometric point of the base, the fiber is classically simple. In various examples, this verification reduces to something that people in differential algebra have already verified, because the fibers. So if you're thinking of this as a parametrized family, then people have already studied specific fibers and their PV theory. So these conditions are usually classically already checked. So, but the morphism has to be globally well behaved as well. So eta has to be faithfully flat and either affine or projective of cohomologically flat of dimension 0, or a suitable composite of such. Then we can deduce that eta is a universal geometric quotient. So basically it's going to be stable under arbitrary base change, and therefore it is going to be universally categorical quotient by the previous theorem. Hence, it's categorically simple, has universal pi 0. So that is very effective. As I said, in most examples, the fibers have already been checked by previous researchers. Okay, now we come to the framework for differential Galois theory that allows us to express our main result. So we start with an adjunction where the top category is the category of differential schemes that admit pi 0. And the bottom category is the category of schemes. And then we have the adjunction of pi 0 and the constant scheme functor. And we give ourselves some indexed data on schemes for which we want to develop the Galois theory. That, in the way that I previously explained, gives us a natural way to define indexed data on differential schemes. We also have a pseudo-natural transformation from classical index data on pi 0 of some z to differential index data on z. So this is this all comes out in a completely general functorial way. Now we define a morphism in A of differential schemes to be pre-Picard-Vessiaux for the given index data if F is effective descent for differential data associated to P, and X, X cross X, X cross X cross X are all simple for P. And for suitable P, maybe this doesn't make sense for all P, but only if P is a class of morphisms such that F actually belongs to that class of morphisms itself. We define F to be Picard-Vessiaux if it's effective descent. And this condition we understand very well through the theory of differential descent I explained earlier. Plus, we require X to be simple, which is the same as here, but just one more condition, that F is self-split. It is split by itself. So that condition will automatically imply the simplicity of these other fiber products. In other words, if F is Picard-Vessiaux, it is also pre-Picard-Vessiaux. Now, suppose we take a pre-Picard-Vessiaux morphism. We then know that its kernel pair groupoid actually is an internal category in A, because we assumed that pi zeros of all these objects exist and are universal. So the kernel pair groupoid is a category in there, and we can now apply pi zero to each component. I mean, to the whole diagram, and that gives you the so-called Galois pre-category. When F is Picard-Vessiaux, this pre-category defined here is in fact a groupoid, so it's better behaved. Pre-Picard-Vessiaux corresponds to the Galois theory of separable field extensions which are not normal. So it's not very well known, but you can develop such a theory, except you will not have a group of symmetries, a Galois group. You will have a free category if you want. So our main template theorem, Galois theory of differential schemes, if F is pre-Picard-Vessiaux, we have an equivalence of categories of objects which are split by F and of the actions of the Galois pre-category in P. And of course, if F is PV, on the right-hand side, you get groupoid actions, which are better understood. So you'll notice immediately that this, the form of stating this Galois theorem is different from the classical PV correspondence. So you might ask, naturally, as Akira Masaoka did, can you actually recover this equivalence? And not only that, we were able to sort of improve it, or improve the understanding of the classical PV correspondence. So let me explain this. As before, we have our base differential field, say characteristic 0. K is the field of constants, and for brevity, the spectrum of K is denoted S. Now, let's take a morphism of differential schemes to the base, which is spectrum of the base field, such that X is classically simple. So it's kind of very near the usual condition of a simple ring. For example, if you take X to be spectrum of a PV ring, it will satisfy this condition. But also, you can take X to be the torsor for the strongly normal theory of Colchin. It will satisfy this. And you also ask F to be self-split, which again is satisfied by both cases. Then the conclusion is F is Picabessio in in the categorical sense. The Galois groupoid is actually an S group scheme, and we have a correspondence between split quasi-projective quotients of the torsor and all closed subgroups of the Galois group. Now, you might ask, what about the classical correspondence between intermediate differential fields? Well, it's actually here. So if you take the function field of X, that's going to be L, the PV extension, and then the intermediate fields are going to be the function fields of these quasi-projective quotients. So we can say that this theory unifies the linear PV theory and also strongly normal theory of Colchin. So now I can proceed with the various examples and show you how we can treat a family of parametrized strongly normal equations. So the base, the algebraic geometric part of this is simply the Weierstrass family of elliptic curves. So you can think of E as being given by the equation y squared equals x cubed plus ux plus v, where u and v are parameters from the parameter space X. And all right, so then y is obtained by adjoining a differential variable z, and we impose that the derivative of z is 1. And on x, we impose a differential structure, which is essentially equivalent to giving a logarithmic differential equation on x by the equation logarithmic derivative equals alpha for some non-zero alpha. And okay, what can we then prove? We can prove that this S really is pi 0 of x and pi 0 of y, and x is simple. How do we see this? Because if you study geometric fibers of x over S, they are already studied by Colchin for particular choices of parameters, you see. So this point in the base simply chooses the particular choice of parameters for u and v. And this is already proved to be strongly normal by Colchin, and we have classical simplicity. And the self-splitting at the algebraic level, because x is defined as the pullback of this diagram, at the algebraic level of underlying schemes, it's completely obvious. But you have to check that also the differential structure is compatible, because here you have x delta cross x delta, and then here you have x delta, and then everything else is constant. So, however, you can just check this through an easy calculation with invariant differentials. From this, we conclude that f is Picabessio in our categorical sense, and the calculation tells you that the Galois groupoid is basically E over S. And if you think about it, these are the same morphisms, so this is just a group scheme over S. We have a specialization result, which says that as you vary the parameter over the base, the Galois Picabessio Galois group, which is the classical one, can be obtained by specializing, by taking the fiber of our Galois group at S, and it is as it should be. It's the elliptic curve ES itself. So it shows you that our more general Galois group specializes to the appropriate ones in the fibers. Okay, so this is the beautiful application that Sonia Rueda pointed out to me. So it's spectral problems concerning commuting differential operators. So for a base differential field and K its constants, we consider a differential operator L, which has a non-trivial center. It turns out that this is extremely rare, and by the work of Burchnall Chandy, there's a polynomial relation between L and M. Now, if you choose somehow the minimal generator of the center, then the center itself has the structure of polynomial algebra mod, this ideal generated by the BC polynomial, which, if you think about it, looks like the coordinate ring of some curve. So you have this spectral curve, which is the spectrum of the center of L. And why are we calling them spectral problems? Because you can study the joint eigenvalue problems for this L and M, if and only if the point lambda mu lives on the curve. And in the special case of a Schrödinger operator, which is this second order operator, and U is a potential coming from the famous KdV hierarchy, let's denote its associated spectral curve by gamma. Morales, Ruiz, Rueda, and Zurro define the notion of a PV extension associated to this problem, to this spectral problem, in the following way. So they consider the base field to be the function field of the curve base changed to K. And then they take the fundamental system of solutions of the spectral problem and adjoin them to this field. And they're able to prove that you can find such a fundamental system of solutions where the constants of the extended field agree with the constants of this, and it's just the function field of the curve, of the spectral curve. So the hope is that our context will allow you to work not just generically over the function field of the spectral curve, but over the spectral curve itself as a scheme. So we will be constructing a PV morphism from some universal solution scheme to the curve base changed to K in such a way that the pi 0 of x equals pi 0 of y is exactly the spectral curve. And then you will have a specialization result to various points of the spectral curve. Okay, the final example I have is how to treat a linear ODE through not the non-canonical Galois group, but through a canonical groupoid. So I'll explain the PV groupoid of the area equation. So the relevant PV morphism for the area equation goes from X, which is A1 times GL2, with the appropriate vector field that encodes the area equation. This is the universal solution algebra for the area equation. And we can prove that F is Picabesiau in categorical sense, which gives us a Galois groupoid. So you see, in this case, pi 0 of x is bigger than pi 0 of y. So that's why we get a groupoid and not a group. And when you calculate those, we see that pi 0 of x is GL2 mod SL2, which is the multiplicative group. And here we obtain GL2 cross GL2 mod SL2. And if you think about it, the choice of a PV extension corresponds to fixing the value of the Wronskian as a value in GM. So this object of objects encodes all the possible choices of Wronskians, in other words, all the possible choices of Picabesiau extensions. And this object code between PV extensions. And this gives you a perfect analogy between an idea that you can extrapolate from Deligne's fundamental groupoid of a Tanakian category from his famous paper, which, if you adopt a Tanakian approach to PV Galois theory, will precisely do the same. So in his approach, the object of objects will be the collection of all fiber functors, which of course we know corresponds to choices of PV extensions. And these are all isomorphisms between different fiber functors. In other words, isomorphisms between different PV extensions. It is just that our approach is somehow more direct and more geometrical than the Tanakian approach. Okay, so let me finish by talking a little bit about the forthcoming work. We showed that differential Galois theory can be broken into two conceptual parts. The understanding of some pre-categorical form of descent theory, plus the categorical Galois theory in its indexed form. And the same template will work for any other types of structures which can be encoded through pre-category actions. So in other words, we can do exactly the same and apply it to difference PV Galois theory, except we need to use lax actions, which presents some technicalities from the category theory perspective, but we already established all these from a category theory perspective. But also various common generalizations, such as the theory of differential equations with difference coefficients, familiar from Divisio, Ardoin, and Widmer, or differential equations with differential coefficients, such as in Cassidy-Singer, partial derivatives case or partial difference operators case, Hasse-Schmidt systems of derivatives, or something even more general. And as I said, we're hoping to confirm these applications to the problems of commuting differential operators, spectral curves, and perhaps even enhance some of the understanding of integrability. And next, we would also like to climb higher in the direction of higher category theory. As I mentioned, pre-categories that we use heavily are truncated simplicial objects to level 2, and we hope that by studying higher levels, we can develop some interesting Galois theory as well. So thank you very much for listening.
Thank you. Do we have any questions for Ivan? Feel free to unmute yourself if you have any question. So I have one. The PV groupo you mentioned in your last example, is that exactly the same as the Malgrange groupoid that, for example, Guy Gassal has looked at?
No. You see, in this case, our groupoid is what people would maybe call action groupoid for SL2. But Malgrange from Guy Cassal and others' paper looks like this. So both of them somehow make it clear that SL2 is the key group, but they look different. And yeah, we'd like to understand what's going on and how they compare.
And that's not done yet.
We haven't done that yet,
Okay.
no. Basically, because of our lack of understanding of Malgrange side, but we'd like to, as soon as we kind of find some time, we'd like to understand this part and see if, you know, I think Umemura, one of his very late in his career papers, was somehow where he expressed his frustration that he did not fully understand Malgrange's theory, and that while being analytical, he could not fully incorporate it in the algebraic world, but somehow seems to achieve better results. So we'd like to understand that and maybe see if we can somehow incorporate it in the algebraic geometry world.
Thank you. Are there any other questions for Ivan?
I have a question.
Go ahead.
Yeah.
If x to y is Picard-Vesiel, and you have something intermediate, maybe x to z to y, is x over z automatically Picard-Vesiel?
Yes. I mean, you have to you have to ask maybe for some flatness. Yeah, but in this case that I described, it will be the case. Yeah. So basically, this is PV. So then this will also be PV. So it's somehow it provides this missing.
So is the groupoid of x over p a quotient of the groupoid of x over y?
Yes, exactly. So this is the, yeah, you see, this is the connection. So for p, your x to the p is also PV, and the corresponding subgroup is the Galois group of that, and then the quotient will, yeah. So if p is also PV over y, then you get the corresponding calculation for the quotient. And I think this cannot usually be done in ordinary PV theory with fields, because if we're to follow Genelidze and this has to correspond to the ring, then there's no notion of ring being a PV over another ring. So I think our added generalities removes this problem. Did I answer your question?
Oh, yes, thank you very much.
Thank you.
Great. Any other question to Ivan? If not, let us thank him again.
With me? Hello? Yeah,
Yeah,
I
you have a question? Yeah. Sorry.
I don't know if it make any sense. How do you put the strongly normal extension? I mean, what is the morphism? When is the morphism being strongly normal?
So, okay, let me. Well, we didn't define the. So we have a more general notion of a Picabessian morphism, which includes the morphism that you get in the strongly normal theory when for X you choose the torsor for the strongly normal Galois group.
Okay.
Yeah. So it's not that we're not recreating the strongly normal theory from scratch. We're using the Colton's result, which says that if you have a strongly normal extension K to L, then there exists some X scheme, and there exists algebraic group such that group acts on X, and X is the torsor.
Okay.
So when you choose that particular X and form this morphism, then it fits into our definition of PV.
I
PV
see.
morphism.
Okay.
Yeah. So PV morphism can be a lot of things. So as you can see, it can replace strongly normal torsors, but also in this last example of airy groupoid, it allows the possibility. So in this case, pi 0 of x is not the same as pi 0 of y. And this is not allowed in PV theory, typically. So, but for us, this is almost a feature, because then you're getting a non-trivial groupoid rather than just a group scheme. Did I answer your question?
Well, I suppose.
Yeah.
I mean, well, okay, never mind.
Maybe our choice of names is not correct. Maybe we should have called it differential Galois morphism rather than PV. But I thought in honor of Picard Monsieur. But it can be quite different from the usual PV ring to ground field, like here. I mean, I didn't show a slide which because it's rather technically tricky, but I think I have it at the end of the somewhere. Let me see. Right. So you cannot get much further with quasi-projective morphisms, but because there's no for descent theory of quasi-projective morphisms, we are using very heavily that the base is a field. Now, there is a descent theory for polarized quasi-projective morphisms over arbitrary schemes, but then the theory has to take a different flavor. So basically, here's the sketch of some kind of polarized quasi-projective Galois theory, which can work over an arbitrary base scheme and over an arbitrary scheme of constants.
Okay, thank you.
Thank you.
All right, great. Okay, so I think it's time we can say thank you again to Ivan. It's a nice talk.
Thank you very much. Looking forward to seeing many of you as soon as possible, possibly in Dart. And goodbye.
All right, bye-bye. Thanks.